Welcome, everyone. Thank you for joining us today. My name's Lori Cook. I'm the Manager of Educational Outreach with AWC. Our program today is CLT Connection Design Provisions in the 2018 NDS. This program is copyrighted, and it is AIA accredited. Amongst the other programs, we are required to show that slide. We have our disclaimer that's required by our lawyers, so if you would like to read the fine print, you can go ahead. One thing we like to point out is the webinar is being recorded, so if you remain a participant, you will consent to being part of such a recording. If you do not consent to being recorded, we ask that you disconnect from the session. The course description is here. I'm going to assume that everybody took a look at the course description when they signed up, so I won't spend too much time reading that or the attached learning objectives to you all as well. But the first thing we're going to do to keep everyone engaged today is our first poll question. So I'm going to ask Marcy to go ahead and launch that one. And this one's always the easiest because any answer you pick is correct. And we'll wait about 30 seconds as usual for everybody to have time to respond. All right, great. So we can go ahead and close that out if we're ready. And we'll share the results. So, all right, we have, as I expected, a large contingent of engineers. This is going to be an engineer-heavy topic. We've got 21% of you are code officials, and then we've got a variety of everybody else, a small percentage. So thank you, everyone, for joining us and for your attendance. And great. So our outline slide today here. I'll start with a brief introduction, just some background information on, some CLT provisions, what it is, and a couple of code references. But for those of you that are more interested in learning about mass timber products, we obviously have been doing quite a few webinars on this product, and we have several coming up that Marcy was talking about earlier. So definitely check out our website for more information. I'll address some of the 2018 NDS references that are relevant for both mass timber and connection design. And then we'll go into some of the fire design provisions, both in the NDS and in Technical Report 10. TR10 is a supporting document that is available on AWC's website and provides some additional information that supports the code provisions and goes very in-depth and provides a lot of commentary and some other useful things that we're going to talk about. And then we'll wrap it up with a couple of connection design examples. So the ones we're going to do today are fairly elementary. There won't be anything too crazy. We're not throwing any curveballs. So these will be kind of just basic connection design examples. So, and for those of you that have been on some of our other connection webinars, you'll probably be familiar with hearing me talk about proprietary fasteners versus standardized fasteners. And for the NDS design provisions, the chapters that we talk about connections, these are applied to standardized fasteners. Specifically, we're going to talk about Chapter 12 today, which is our dowel-shaped fasteners chapter. So when we go into Chapter 12, we see that the various types of fasteners have relevant standards that govern the size of the fastener. There's requirements on things like the dimensions of the nail head and how much of the lag screw is threaded and all of that. So when we talk about proprietary fasteners, we don't have design values included in the NDS for those. They are covered by some language in NDS 1.1.1.5, which states you are permitted to use materials that are beyond the scope of the NDS. However, they would need to be approved by your authority having jurisdiction, obviously. And you would need to get the installation and the calculation and design values and things like that. That would come from the manufacturer. So if you're using some sort of proprietary fastener, such as something that might look like one of these types of fasteners, the design, the installation for these proprietary solutions would always be per the manufacturer's specs. So we commonly see different types of fastener solutions for the different types of panel joints we have, and here's some examples of different types of fasteners. You see where we've got panels intersecting at 90 degrees. So, something like a wall floor connection or a wall ceiling connection. And you see these types of kind of steel angles. This one on the bottom in the middle here is a really long lag screw that's being installed at an angle. So, these are typically connections that do go in very quickly. So that's something that the ease of installation is something that is a benefit of mass timber. Where we have panel butt joints, you also have some different options, and different manufacturers have different preferences, and this is just something that as a designer, you'll hear me probably say this several times today, but as a designer, you'll want to discuss with your CLT manufacturer, which types of panel joints are most appropriate and how you would need to model those. So these types of CLT panel joints would typically give us a kind of an ordinary system for seismic design purposes. So that doesn't complicate our analysis unnecessarily. So, but you'll see that there's options such as splines or lapped connections, and again, just kind of depends on the manufacturer and the situation. Different CLT manufacturers will also provide different detail options for other types of connections. So this is an example that comes out of a manufacturer's catalog of some of their construction options. So, for example, on the left, you'll see kind of a ledger type connection where we've got a CLT floor panel coming into a wall assembly. On the right, you see that's a kind of a post and slab type construction. And the designers, again, the sooner that you can talk to the CLT manufacturer in your planning stages, the better it will be for the design of your structure, because you can work around things like fitting connections into assemblies, and especially when you have fire rated connections, these can be a little bit complicated to fit in if you don't account for it early in the design. It can create some unnecessary challenges. There's also a wealth of quote-unquote pre-engineered connectors showing how CLT panels can interface with other products that aren't CLT. So, for example, you might have a CLT wall interfacing with a concrete slab for a podium or for a foundation or for whatever reason. And then on the right, you see a glulam supporting beam and a pre-engineered connector that would be used to fasten that glulam support to the CLT wall and then provide support for the CLT floor panel. So you'll see a lot of use of different types of hardware. Most of it probably right now is proprietary, but there are some lag screws and other standardized fasteners that also could work as well. Jumping into the 2018 NDS. So those of you that are familiar with the NDS are familiar with the layout. We have 16 chapters. Of those, Chapter 10 is the newest chapter. Chapter 10 was first debuted in the 2015 NDS. Well, we had a Chapter 10 before, but it's Chapter 10 as the cross-laminated timber chapter was introduced in the 2015 NDS. And then if you paid attention in our 2018 NDS update webinar earlier, you'll know that there were some refinements made in 2018. And that covers the design criteria for the structural design of cross-laminated timber. Chapters 11 and 12 are where we get into some of our connection chapters. So chapter 11 is our mechanical connections chapter. So that'll apply to pretty much any type of mechanical fastener that's covered in the NDS connection chapters. Now, the next few chapters are the different types of connectors. We're going to primarily be in chapter 12 today dealing with dowel type fasteners, but as you can see, the NDS also has chapters for things like split ring and shear plates and timber rivets. Going into chapter 10, like I said, this is where we find the provisions for CLT structural design. We find our adjustment factors for our design values. The design values would be coming from the manufacturer, and then the appropriate adjustment factors would be applied depending on if you're using an ASD or an LRFD format. And similarly, Chapter 11 has an adjustment factors table. And like I said, Chapter 11, this is going to be the provisions for all of the mechanical connectors in the NDS. So that's going to include our dowel type fasteners, obviously, but you also see here we've got provisions for the other types of fastenings, these split ring, timber rivets, spike grids, and such. Chapter 12 is where we go for our dowel-shaped connectors, and there's a few others, but the primary ones, the most common types of dowel-shaped connectors that most engineers are dealing with are these four. There'll be nails, wood screws, lag screws, and bolts, and we detailed earlier the relevant standards for the manufacture and sizing and such of these types of fasteners. Now, when we're dealing with withdrawal loads, in CLT, the procedure for calculating the withdrawal capacity doesn't require any sort of special modification when we're doing a CLT panel. So if you've done one withdrawal design, you've done them all. They're going to be the same whether it's a nail in a piece of solid stone lumber or the same equations would be used for what you'll see. The procedures don't require modification. Shear capacity is a little bit different, and we're going to take a look at that because the shear capacity calculations require that we adjust the main member bearing length, and that's detailed in NDS 12.3.5.2. And the main member bearing length is going to be adjusted based on the specific gravity, or essentially the species and the specific gravity that the CLT is constructed out of. Some other things when we go into Chapter 12, we have our C sub delta factor, our geometry factor. For fasteners that are 1/4 inch in diameter or less, C sub delta is equal to 1. So when I talk about calculating C sub delta required end and edge distances, that's primarily going to be for fasteners that are larger than 1/4 inch in diameter. So when we have fasteners that are larger than 1/4 inch in diameter and the connections are going through the panel face, that would be designed per the regular provisions of NDS 12.5.1. If we're in the narrow face of the CLT panel, the panel edges, you have to go into NDS 12.5.1.4, and that's going to give you provisions that apply to things like spacing, end distances, and edge distances for the fasteners. And again, that's only for the narrow edges. So if you go into that section in the NDS, you'll see that we have the table shown here that provides your end distance and edge distance spacings, your spacing in a row, and obviously depending on which one you're calculating, it can depend on the loading. Now, it may not always be the most intuitive thing to determine which way am I loading it compared to what. So we do have some illustrations here in Figure 12I to make this a little bit more clear. But as you can see, regardless of the loading direction, the edge distance is constant at 3 fastener diameters. And then the spacing for fasteners in a row is 4 fastener diameters. And then the end distance will vary between 4 or 7 diameters depending on the direction of the loading. So with that, let's launch our second poll. And we'll give it a few more seconds to let a few more folks vote. All right, great. I think we can go ahead and close it out. And here are the results. Great, so looks like we had about 19% said A, 74% said B, and 5% said C, and 3% D. So let's take a look at the answer. All right, the answer is 4D. So that one wasn't one that we needed to be clever or anything like that. We just had to look at the table. So spacing for fasteners in a row, and that's, again, that's for the narrow edge of a CLT panel. Those provisions wouldn't be in force if you're designing something through the wide face of the panel. Okay. All right, our next section we're going to talk about are some of the fire design provisions in both the NDS, and then we're going to discuss some of the provisions in Technical Report 10. So NDS section 16.3 is where the requirements for connections come into play. So it states that connections that are between members which are required to be fire resistance rated must be protected from fire exposure. And we have these different options for how we can provide that protection. So we can provide it by providing additional wood cover beyond just the wood members in the connection itself. But it is important to note that we have to protect not only the fastener, but also the wood that is part of the connection. So that's the part of the wood that the screw or the nail or whatever is biting into. So we need to keep that in mind when we're in our design. So we can use just additional wood cover. That's totally okay, as long as it complies with other relevant code requirements. We can use a fire-rated gypsum board like a Type X, or we can use some other approved materials, some coatings or insulation or whatever. There's lots of different products out there. Or you can use a combination of those options. So what we see, kind of often is that, you might have a layer of 5/8 Type X and then some additional cover provided by the wood material. Now, when we get into the 2021 IBC, I just wanted to give everyone a brief reminder of these new mass timber building types that are coming. We have Type 4A, Type 4B, and Type 4C. Our good friend, our old Type 4 construction has been renamed. That's going to be Type 4 heavy timber. So nothing has changed about our historic Type 4 heavy timber building types. So these are the new mass timber construction building types. And there's, like I said, multiple webinars that AWC has done and will be doing talking about these building types as we lead into the 2021 IBC. But the fire resistance rating requirements are ranging from 1 to 3 hours with various levels of non-combustible protection required. So, for example, a Type 4C structure, you can have your mass timber exposed pretty much anywhere except for shafts, concealed spaces, and the outside of exterior walls. Whereas a Type 4A structure, you have to have 100% non-combustible protection on all surfaces of your mass timber. So your Type 4A structure is obviously going to allow you to go taller than Type 4C structure, but there's trade-offs with the amount of mass timber that can be exposed and things like that. So if we go into section 2304.10.1 in the 2021 IBC, we see that the requirements for fire resistance rating of connections, we have a couple of different options. You can do testing. However, it's really not feasible to test every single connection out there. But we also can do engineering analysis, and we need to demonstrate that the temperature rise is contained. So you'll see that the average temperature rise has to be limited to 250 degrees Fahrenheit and a maximum temperature rise of 325 degrees Fahrenheit. And that's for the entire time that the fire resistance rating of the structural element is. So it would be for, a 2-hour rating, you would need to limit that temperature rise to 250 degrees for 2 hours for the average. Sometimes you'll see that special adhesives or sealants might be required to resist the passage of air at the intersections of panels or at beams or at columns. That's something that you might need to have inspected per the special inspection requirements. So we're going to just take a brief look at those there. So this is an example of some sealing that would be called for the prevention of passage of hot gas or hot air through the spacing between the beam and the panel, and the panel or the column, things like that. 1705.19 does require special inspections of sealants or adhesives as they are installed. You can see the adhesives in this picture, but typically after installation, that's not something that you would leave exposed. From an architectural standpoint, it may not be the nicest thing to look at. So other than when you've got adhesive anchors resisting sustained tension loads, you would only need periodic special inspections of your connections. And the reasoning for this is most of the connections associated with these new mass timber elements are the same ones that were very similar to the ones that we've used in traditional heavy timber. So, things like screws and bolts, installing a screw or a bolt in a CLT panel is not that drastically different than installing a screw or a bolt through a glulam beam, for example. So that would be something, again, that would only need periodic special inspection, but if you are using an adhesive anchor under sustained tension, that's something that would be necessary to have continuous inspection. As I mentioned, the new section that deals with the special inspection requirements for these new mass timber construction types are contained in section 1705.5.3. Primarily, there's a table in there that's got the same number that has all of your special inspection requirements for these new mass timber construction types. Again, that's only type 4A, 4B, and 4C. This doesn't require any changes to the way that the type 4 heavy timber structures are constructed. So I promised some discussion on Technical Report 10. It was recently updated. I believe the update was posted in maybe late May or early June, so it's freshly updated, and it contains a lot of in-depth information on the NDS Chapter 16 provisions. So to help designers kind of understand where these provisions are coming from, why they are the way they are, and it also provides information on not just exposed wood members and assemblies, but protected wood members and assemblies as well. There's also information on protected wood connections of those fire resistance rated members. And there's a really extensive commentary and some really good example problems. So I won't get into too much on TR10 today, but It also provides guidance on detailing wood members and protection to account for something that's known as char contraction, where the edges of wood elements abut. So like if you have the edge of a beam and column interface, for example, the potential effects of char contraction should be evaluated. So when we talk about char contraction, we need to kind of understand some of the basics of the way the fire would propagate through the connection. So we talk about the char depth, and that's the distance between the original wood surface prior to fire exposure and the location of the char front. And that char front is defined as the furthest extent of the charring into the wood. So as the wood chars, its volume decreases, and then the thickness of the char layer, the thickness of the char layer is then becomes less than the thickness of the char depth. And then this difference between the depth of char and the thickness of the layer, so obviously you have some of the char that falls off or dissipates or is consumed. So this difference between the char depth and the thickness of the layer is approximately 0.3 times the char depth. So that's that linear relationship between the char depth and the char layer. So this phenomenon results in the formation of a wedge-shaped gap, and that can propagate along the interface between the two wood members. And you can see that wedge-shaped gap forming at the bottom here of this connection in this illustration. The ignition would then extend into the gap that is, some distance that's water. So and then as a result of this ignition extending into the gap, we need to provide additional wood cover or blocking to protect the area around those abutting edges. The fasteners that you're using to attach that protection don't require additional protection, because then you just kind of wind up with an iterative process. So this is an illustration in the new updated TR10 that kind of illustrates that concept of char contraction, and it goes into some further depth on calculating how much wood protection would be required for a given fire resistance rating. So I know that was a little bit of a heavy explanation, so let's go ahead and take a breather for a minute and have a poll question. All right, great. We're at about 80% have voted, so we could probably close that out. And let's see. We have 78% of you said it was false and 22% said it was true. So the majority are correct, so congratulations. And then we'll go ahead and hide that. All right. So the answer is false. So this one was a little sneaky, but additional wood cover can be used to protect the connectors and fasteners from fire exposure. So it can be a combination. It can depend on the requirements of the building type, but you can use additional wood cover to protect a fire resistance rated connection. Great. All right. So with the rest of our time this morning, we're going to go into our connection design examples. So the first design example is our withdrawal example. And if you're paying attention, when I mentioned that if you've done one withdrawal example, you've done them all, this one might not be super exciting to you, but we'll do it as an exercise anyway. So we're just going to determine the unadjusted withdrawal capacity for a standard lag screw. The main member we're going to use for this example is a 5-ply SPF panel. We're going to assume each ply is 1.5 inches thick, so we have a 7.5-inch thick panel. You, depending on the species, may have differences in the thickness of the plies. Typically, southern pine would be like 1 3/8 inches for each ply or each lamination. So you'll want to verify that with your manufacturer. In this example, we're just going to use a 1/4 inch ASTM A36 steel plate as our side member. And when we go into Table L2 in Appendix L in the NDS, we can find our dimensions for a standard lag screw. That's, again, that ASME standard B18.2.1. For today's example, we're going to just use a 3/8 inch diameter screw that's 6 inches long. And we want to pay attention to this T minus E dimension that is specified in Table L2. And what that is the thread length minus the tapered tip dimension. So you see it shown here in this illustration. So that for us is going to be the main member thread penetration. So this is something that oftentimes trips people up. We have a 6-inch lag screw. It's only got a 1/4 inch steel. So let me jump back to the illustration. We have a 6-inch long lag screw. It's only got a 1/4 inch steel side plate. So we've got 5.5 plus inches, not including the tip, of penetration into the main member. But the only part of the shank of the lag screw that we're going to count in our withdrawal penetration is that T minus E dimension. It's the threads. So the smooth part of the shank is not assumed to provide the resistance. So we need to pay attention to our main member penetration as well as how much of that is the thread. Our NDS equation that we use is 12.2-1 to calculate the W value, and that's just based on the specific gravity of the main member and the diameter of the fastener. So we had a 3/8 inch diameter fastener. Our main member specific gravity for spruce pine fir is 0.42. So we just do a plug and chug, and we get W equals 235 pounds per inch. And remember, that's per inch of main member, in this case, in main member thread penetration. So that's that piece of T value that you see defined here. The total resistance of that lag screw to withdrawal then is the W value times the main member thread penetration, which in our case was 3 9/32 of an inch. So that times 235 pounds per inch gives us a total resistance of 770 pounds. Now remember, this is just the unadjusted design value, so depending on your end use conditions, you'd have to go into NDS table 11.3.1 and get the appropriate adjustment factors for your equation, or I'm sorry, for your design value. So it would be based on things like load duration, moisture content, things like that. So this is just the unadjusted design value. So as I mentioned before, for shear design, we do have some slight adjustments that we need to make from our typical yield equation method that we're used to. They're very minor. So to change it up, instead of using the Chapter 12 NDS, I'm sorry, the Chapter 11 NDS yield equations, we're going to use the yield equations from Technical Report 12. This is going to be a bolted equation. It's the grade is the SAE J429 grade 1 bolt, and that is in line with the ASME standard. Our main member is a 5-ply Southern Pine CLT panel, and as I alluded to earlier, those plies are a little bit thinner than spruce pine fir. They're only going to be 1 3/8 inch thick. So our total panel thickness is 6 7/8 inches. Our specific gravity for Southern Pine is 0.55. And then our side member, once again, we're using that 1/4 inch thick ASTM A36 steel plate. Some connection parameters. Technical Report 12 has a benefit over the NDS equations, the yield mode equations, in that your members are not required to be in direct contact. There actually can be a gap between the two members, and the equations in Technical Report 12 are designed to accommodate that gap. In our case, we don't have a gap in this example, so our gap distance is just equal to 0, but we still need that to plug it into our equations. For the ASTM A36 steel, our dowel bearing strength is 87,000 psi, and that can be found in both Technical Report 12 and in the NDS reference. Our grade 1 bolt dowel bending yield strength is 45,000 psi. For those of you that downloaded the slides early yesterday, I had made a mathematical mistake. I had pulled a wrong value out of a table. So some of you may notice that these dowel bearing strengths are slightly different. So I apologize, but these ones are correct. So we have our dowel bearing strength perpendicular to grain, and both of these come out of the NDS in table 12.2.3. Our perpendicular to grain bearing strength is 5150 psi, and our parallel is 6150 psi. And we have our L sub S, that is our side member bearing length. It's just the thickness of the steel plate, so it's 1/4 inch. The main member bearing length, this is where that slight adjustment to our procedure that we're used to needs to come in. So we need to adjust it per the requirements of NDS 12.3.5.2, and that requires that the layers that are loaded essentially perpendicular to grain will have their thickness adjusted by the ratio of the perpendicular to grain bearing strength to the parallel to grain bearing strength. And rather than trying to make heads or tails of that, let's just jump back to our illustration really quickly. We see we have 5 plies, and we're assuming that the outermost plies have the boards running in the up and down direction, and then you see the center ply also has the boards running in the same direction. Plies number 2 and 4 that we see with our X's here, those would be oriented 90 degrees. So those are the plies that we're going to need to adjust the thickness of in this example. So we know that each lamination is equal to 1 3/8 inch thick, so that's our T value, and we just adjust the ones that, again, were oriented perpendicular, so that would be 2 and 4. So each T value represents the thickness of that individual lamination. So you see 1, 3, and 5 are unadjusted, and 2 and 4 are adjusted based on that ratio. And we get an adjusted L sub M equal to 6.43 inches. So now we can roll through our TR12 equations. We need to determine the main and side member dowel bearing resistance, assuming that our fastener diameter is 1/4 inch. And then we calculate the main member, the CLT member bearing resistance based on the parallel to grain bearing capacity, because we've adjusted those plies that are loaded perpendicular to grain. So we don't need to make any further adjustments for the bearing stresses or anything like that. We can just treat the whole panel as if it's loaded parallel to grain. Our side member is simply based on that F sub E, that dowel bearing strength of the steel side plate. And we also will need to determine the R sub D values that are in the NDS table 12.3.1b. what these do is they convert the p-value that we're going to calculate in TR12 to the NDS equivalent z value. So you need to know the theta value, which is the angle between the direction of the load and the direction of the grain. In our case, they're coincident, so that angle is 0. And then we can calculate k sub theta based on that angle. And our modes, our adjustment value, our R sub D value, varies depending on which mode we're talking about, but you can see each of them are calculated here. If we go into Technical Report 12, we can see that we're in a single shear equation, or a single shear situation, so we're going to use the equations that accommodate that. And you'll see that they're actually based off the use of the quadratic formula for modes 2 through 4. The inputs for what A, B, and C are equal to are shown in the bottom part of this table. So we've shown our calculations for our Q sub S and our Q sub M. The L sub M is just that adjusted main member bearing length. L sub S is our side member bearing length. And again, that gap was 0 inches. That's the gap between our members. The Technical Report 12 also gives you equations to calculate these bending moments, the side member bending moment and the main member bending moment. But these are the results that you get when you use the Technical Report 12 equations. So you'll see we have our p-value in the first column that is based solely on the equations from Technical Report 12. We divide those by the R sub D value from NDS 12.3.1, and we get the NDS equivalent Z value. We take the minimum of these, which is, in this case, a mode 4 failure, and that gives us our connection capacity. So for this example, that would be 256 pounds in shear. And as always, these are, again, the unadjusted design values. If you are going to use adjusted design values, you need to provide those adjustments in accordance with the NDS Table 1131 design values based on your end conditions. All right, we've got one last poll. And go ahead and launch that. All right, cool. Okay, everyone should be seeing this. When calculating withdrawal capacity of a lag screw, the capacity is based on the blank of the screw. So is it the deformed shank length? Is it the side member penetration? Is it the length of the tapered tip? Or is it none of the above? And based on the early responses, we have a definite favorite. All right, we'll go ahead and close this out and share the results. So we had a vast majority, 69% said it was choice A, the deformed shank length. 10% said side member penetration. 6% said length of the tapered tip, and then 15% said none of the above. So the actual answer is the deformed shank length. So that was that T minus E dimension, or the length of the threads in our lag screw. So most of you got it right, so that's excellent. Everybody's paying attention. All right, so we're gonna spend the last 12 to 15 minutes today just doing some FAQs, and I do appreciate everybody sending in their questions prior to the webinar, and that helps us get some good discussion points going beforehand, before we open it up to everybody else. But so some of the questions that we received coming into this webinar were, what other items would I need to consider when I'm designing my connection? And as with any timber connection, you need to consider shrinkage. So, don't ignore the perpendicular to grain movement of the wood fiber as it varies with moisture content. A lot of times designers are assuming that, their material's getting delivered to the site with 15% or less moisture content. And oftentimes that's not really an appropriate assumption. So, talk to your manufacturer, see, what is their typical moisture content at delivery. It may not be 15%. It could be, 16, it could be 18%, and still, it would still be considered kiln dried, but it might not, be what your initial assumption was. And several percent moisture content loss can have an impact on the perpendicular to grain dimensions. So you need to have connection details that won't restrain the wood as it swells or shrinks. And that's not something that's unique to mass timber. That's something that you need to accommodate for all timber connections. Another thing that is important is when you're interfacing different materials. So, principles from steel and concrete don't always translate directly to designing wood. You can put big movement joints in steel and concrete buildings, but sometimes movement joints in wood buildings are not always accommodated the same way. You're going to have different coefficients of thermal expansion with wood and steel and concrete. So those are things that depending on the needs of the structure, that could become relevant. And as always, there's aesthetics. As structural engineers, that might not necessarily always be our primary concern, but we have architects that we have them for a reason, and they help make our buildings look nice. So we definitely need to accommodate the aesthetics of the structure. Another question that we have been seeing a lot of lately are there design provisions for CLT shear walls and CLT diaphragms? So the current answer is that it's currently not standardized. Some manufacturers might have data, but what is coming is the 2021 Special Design Provisions for Wind and Seismic, or you might hear me refer to it as SPDWIS. The 2021 Special Design Provisions for Wind and Seismic will have design provisions for CLT shear walls and CLT diaphragms. It also appears that ASCE 7-22 will have seismic coefficients for CLT shear walls based on the 2021 SPDWIS. How the 2021 SPDWIS is going to be referenced in the 2021 IBC. However, the earliest that ASCE 7-22 is going to work its way into the IBC is probably going to be 2024. So there are provisions, they are coming, but it's certainly not as smooth and fluid as some of our traditional shear wall designs that have been codified and have been in the standard for many years now. So Michelle, that is all I had as far as slides. So let's have everybody stay on. We're not quite at our hour yet, so we need everybody to stay on until the top of the hour. But we are going to have some question and answer, and then after that, I believe Michelle will close us out. So Michelle, did you want to come on and see what kind of questions folks have had while I've been talking?
Yes, actually there's some pretty good questions that have come in. And first question is, where can you find more resources about tall wood mass timber?
All right, that one.
Maybe on the...
Yeah, I actually have the website up on my browser here. So if you go to awc.org/tallmast-timber, this is what our website looks like. So it provides a plethora of information. And you can see here on the left, we've got some information from fire testing. We've got some code change information, the code changes that came through in the IBC 2021. Some additional webinars that AWC has presented on the topic. There's links to those there. So there's a wealth of information that I probably could spend another hour talking about just what's on this webpage. So I would encourage everyone, the website again is awc.org/tallmast-timber. But that's kind of our central hub for all things mass timber, I'd say.
Right. Good. And then could you also show where people can find the design examples that have been just published?
Oh, sure, yeah.
When was it published? Because that has information on CLT and connections and all that.
So the new design examples, there actually aren't any CLT design examples in there, but if you go on our front page and click on publications, the 2018 NDS is our latest and greatest, and we've got, scroll down here, we have structural wood design examples. So you can, there's a free view only option. You can purchase a PDF or a hard copy. Unfortunately, this edition doesn't have any CLT design examples in it. I am planning on some updates, hopefully for the 2021 edition, that will include some additional CLT and mass timber design examples, but there are a substantial amount of connection design examples in that document. So I would strongly encourage you, if you are unsure or just haven't done a lot of wood connection basics, there's some equations and things that can seem a little daunting the first time you look at them, but the structural wood design examples will help walk you through some of those.
Okay, and then also one last reference is to 2 webinars that we did last year.
Oh,
or
yeah.
was it this year? Right?
I think
on
one
CLT
was last year.
Walls.
Yeah. So we have
the walls and the floors.
If you click on at the bar at the top, we have our education page, and then we have our e-courses. And scrolling to, we have quite a few on here, but if you, so the CLT, we had a wall program and a floor program.
There.
Yep, so we have DES 441-1 is CLT as a floor or roof element. And then DES 442 is a CLT wall design. So those are 2 additional programs that give some design provisions for the actual CLT panels, something that we didn't really talk about at all today. But if you're interested, they are both available as recorded webinars.
Okay, and here's a question. Could you detail what the term diameter means? The inner diameter, the outer diameter, with relation to the outer diameter and thread?
Yeah, that's a good question. So yeah, we do have, when we look at things like lag screws, we have several different diameters. Primarily, unless it's specified directly, we're going to use the nominal diameter. So that's the D value. So that would be, the 1/4 inch, the 3/8 inch values. There are limited applications where you would use the root diameter, and that would be for instances where the shear plane is passing through the threads. And Technical Report 12 actually provides some nice illustrations talking about that. So if you have, in our example, we had the shear plane of the side member and the main member passing through the unthreaded portion of the shank. So we were able to use the full body diameter, the D value. But if we had had a fastener that, for example, may have been fully threaded, it would be more appropriate in those types of instances to use the reduced body diameter or the D sub R value.
Right. Good. And then as far as the bending yield strength of the fasteners that you're using or specifying, how do you find information on that in the NDS and what's in the tables?
Yeah.
Should engineers specify it on their drawings? And someone asked a question about
Yeah, that's a good question. And actually, Technical Report 12 is a good place to go for that. So if we go on our website here, there is an appendix to TR12 that provides design, some design values for different types of metals for the fasteners. Let me get to the, let's see. Oh yeah, here it's in the back here. Here we go. So you'll see the dowel bearing strength for the materials, and then we also have this table here. Let me make it a bit bigger. That provides our dowel bending yield strength, the FYB value. So it will depend on the grade of the material. It will depend on the type of the material. It'll depend on what type of fastener it is. So there is some information listed in Technical Report 12. If you're unsure, you can also check with the manufacturer of the fastener. They should be able to provide that information. And if all else fails, these equations do work for these standardized fasteners that you see in the NDS.
Okay, good. And the engineer should specify what they're assuming in their design on the drawings.
Absolutely, yes. Especially the grade of the fastener, it can have a big impact on the capacity. So it's important to specify, not only the correct size fastener, but also the material grade.
Right. Here's another question that came in when people were registering, and it says, do you have any information on the status of CLT lateral systems being adopted to ASCE 7?
Yeah, so that was the one I touched on briefly on this FAQ slide. Let's see. So we think it will be in ASCE 722. Well, while that's the next version of ASCE 7, we've obviously been talking a lot about IBC 2021. So with the way time goes, ASCE 722 will not be done before IBC 2021. So the ASCE 722 seismic coefficients for CLT shear walls will probably not be built into the IBC until 2024 because of the way the adoption process has panned out.
Yeah.
But they will be in the 2021 SPIDWIZ. So.
Yes. And just two more questions.
Sure.
One, could you clarify using the C sub D factor in your example? I think there was a question that came in.
Oh, yes. So I actually did not use C sub D, the load duration factor, in my examples because for both of my examples, I was calculating only the unadjusted reference design value. So I did not specify a load duration or type of load. So without knowing that, we would not be able to specify a load duration factor or a C sub D factor for an ASD design, or if you're in an LRFD design, that would be the time effect factor. So that's why we didn't see that appear in my examples, because these are only the unadjusted design values. These aren't for the load, the moisture, and things like that.
Yep. seismic or
Yeah.
snow or whatever.
Yeah.
Okay, one last question. What's the difference between a small diameter fastener and a large diameter fastener? Could you reiterate something about that?
Yeah,
Because we get that question
I
a lot.
didn't touch on that necessarily too much, but the kind of rule of thumb that where the NDS kind of draws the line is that 1/4 inch. So when we look at smaller fasteners, especially in terms of that geometry factor, the C sub delta factor, the line gets drawn at a 1/4 inch. So fasteners that are smaller on the smaller end, less than a 1/4 inch, we don't have to calculate that geometry factor. Larger diameter fasteners, the geometry factor calculation is necessary. So it's not necessarily codified, but that's kind of a rule of thumb. And obviously, it's going to be relative to the dimension of the wood that's being installed in as well. So something in a 2x4, compared to a 10-inch by 18-inch glue lam or something, it's all going to be relative as well. So it's more of a rule of thumb, less of a code, code standard or anything like that.